Let's examine the one sample t-test. That test compares the mean of a population to some other value. We have here an example in which archaeologists have unearthed the humerus bones of an animal species, that's the upper arm bone of some animal species, and they want to know whether or not these bones are the same of some species A. They already know that species A has a mean or average length to width ratio of 8.5. We're going to go into Minitab shortly and find those data. Okay, question A asks us, is there sufficient evidence at a 1% level of significance to say that the newly dug up bones are those of species A? Alright, a couple of things that we're looking at in part A. Number one, when we run this test, we're going to compare our p-value to 0.01 because we're told we want to make our decision at a 1% level of significance, which is another way of saying I want to be 99% confident in my results. And when I get my p-value, the p-value is going to be compared to the 1%, which will be 0.01. Now, then we want to know whether or not these bones represent species A. Well, okay, when we go to set up our hypotheses here, the null hypothesis is going to be that these bones do represent species A, so the mean is equal to 8.5. But if the mean length to width ratio of the dug up bones is significantly smaller than 8.5 or significantly bigger than 8.5, they will not represent species A. So this is going to be a two-tailed test, equal to 8.5 versus not equal to 8.5. Alright, then in part B of this question, if the bones don't represent species A, what can we say about the average length to width ratio for these bones? And when we do that, we want to use a 99% confidence interval. Okay, now another thing to have a look at in this problem is that we are not told the population standard deviation. And if I go to the next slide here, I have some summary stats on the data, and it looks like 41 bones were dug up. We do not know the true population standard deviation, which means we would be using the t-distribution. The t is used when you have to use the sample standard deviation, which is the 1.204, and when your sample size is smaller than 60, which is the case right here. Okay, when we run this test, our null is that the bones do represent species A. Our alternate is that they don't. We calculate a t-statistic this time. We take our sample mean of 9.258, subtract that from the hypothesized mean, and divide by s divided by square root of the sample size, which, by the way, is referred to as the standard error of the mean. That's that whole thing right here. So when I work out the standard deviation divided by square root of 41, that is the standard error of the mean, which when you do summary statistics, Minitab automatically gives you, because it is a calculation that you have to do pretty well all the time. Okay, so we work out the test statistic of 4.031. Now if I go to the next slide, and I was doing all of this by hand, I would have to find the area under the curve to the right of 4.031, but because this is a two-tailed test, I also have to consider the area under the curve to the left of 4.031. And I've done this in Minitab and found the area under those two tails, which is right here at the 0.001211, and I'd have to multiply that by 2 in order to get the true p-value. Now, that's if we're using software. If I was doing this by hand, I'd have to use the tables. Tables, however, are fairly limiting, particularly when it comes to the t-distribution, because not every area is given in the curve, and not every possible degrees of freedom is given in the table. So the best you could do here is you would go into your table that corresponds to the appropriate number of degrees of freedom. We've got a sample size of 41, there will be 40 degrees of freedom. So I go into the row that corresponds to 40 degrees of freedom. These values in here represent the t-values. Notice these t-values get larger as I come this way. I need to find a t-value as close as possible to 4.031, which does not appear in here, but it would be to the right of this 2.704. So whatever value, that 4.031 is going to lie way over here somewhere. All right, now these t-values correspond to certain areas under the curve. Our table gives us area under both tails or area under just one tail. We're interested in both tail areas. And notice that the tail areas get smaller as I come this way. My t-value is 4.031, which is going to be way over here. Whatever the area under the curve, whatever area under the curve that value corresponds to, is going to be a number less than 0.01. So all I know from tables is that my p-value will be smaller than 0.01. I don't know exactly what it would be, which is where the software comes into play, and I get a more correct answer up here of 0.0002422. Okay, I have my p-value. The question then is my p-value less than alpha? And yes, that p-value of 0.00042 is definitely a smaller number than 0.01. And anytime the answer to that question is yes, we are going to reject the null hypothesis. So if I go back up and I look at my null hypothesis, I am rejecting this statement. And basically what it tells me is that the evidence, that is the data, support the alternate statement, that the average length to width ratio of the dug up bones are not the same as the 8.5, which represents species A. What is my conclusion? These bones do not belong to species A. Now, anytime you come to the conclusion that it's not equal to a certain value, generally you want to know, is it bigger than, and I would want to know, are these bones, or do these dug up bones have an average length to width ratio that's smaller than 8.5, or is it bigger than 8.5? I don't know that from the test of hypothesis. Now I could make a good guess because the mean of my sample is 9.258, which is definitely bigger than 8.5, so chances are the bones that got dug up are larger, have a bigger average length to width ratio. But usually we want to stick a number on that, and in order to do that, if I scroll down here, we would calculate a confidence interval. And here's the formula for calculating a confidence interval on a population mean when your standard deviation of your population is unknown. In other words, we have to use the t-distribution. And the way this works out, we have to take our sample mean, which is our 9.258, plus or minus some t-value. Now that t-value has to correspond to a level of confidence. We want to be 99% confident. We want an interval that has a lower endpoint and an upper endpoint, which means it's a two-tailed probability. If my level of confidence is 99, then my level of risk is going to be 0.01, which is this one right here. So I need to be in this column of the table. All right, and then so I know what column I need to be in, and I know I'm dealing with 40 degrees of freedom. What t-value would I use in making my calculation? It's going to be this one, 2.704. So that's where that's coming from right here. And then I got to multiply by the standard error of the mean. Standard error of the mean is defined as the standard deviation of your sample divided by the square root of your sample size. So that's this piece right here. Now, I'll work it all out. What can I say? I'm 99% confident that the average length to width ratio of the bones that we dug up falls somewhere between 8.75 and 9.77. So that gets me some idea of the average length to width ratio of the bones we dug up. The other thing that this tells me is that all these numbers in this interval are larger than 8.5. Therefore, whatever these bones are, they don't represent species A. This species that we've dug up, whatever it is, has a larger length to width ratio than does species A. Alright, so if we were to go to Minitab and see how we would do all this, I've got the file opened up here, file called Bones. The data are all here in column C1. We go to the Stat tab. We are looking for one sample T, and if you mouse over it tells you it determines whether the mean of a sample differs from a specified value. We have our data in columns. I picked that one, so pick the data. I want to perform a test of hypotheses. I wanted to know whether the average length to width ratio of those bones was 8.5 or not equal to 8.5. And because we're also interested in the confidence interval and we're asked to get a 99, I need to change the confidence level. Click OK and say OK. And pay attention to what you have. So this reads as I want it to read, equal to 8.5 versus not equal to. I get my summary statistics, I get my t-value, and I get my p. Now notice that the p-value I get from Minitab is rounded off to 3 decimal places. So whatever my p-value is, it's smaller than 0.000. I need to compare it to 0.01. Anything that's of this order of magnitude is going to be smaller than 0.01. I'll show you in a minute how you could get the more precise p-value if you want. There's our test statistic, which corresponds to what we calculated in the notes, and here's our 99% confidence interval. So if I round that off, it's 8.75 to 9.77, which is what's in your notes. Alright, if I wanted to get an exactly correct p-value, I could use the Graph tab, Probability Distribution Plot, View my probability. I want to see area under the curve. You have to change it from the normal distribution down to the t. We know we're dealing with 40 degrees of freedom. We want to find area under the curve, so that's the shaded area. We are going to give it a t-value. Now I know it says x, but that's just the default in Minitab. Okay, we worked our test statistic out to be 4.031. I plugged that in, and I want to see the area in both tails. And this is what I get. So if I wanted the exactly correct p-value, I would take these two numbers and add them together, or take one and multiply by 2. And that will be my exactly correct p-value. Now, anytime we have raw data, I should have done this when I ran my test first. Going back into my one sample T, I should have a look at some graphs. I could have a box plot, and if you like, we can do a histogram. And let's have a look. So my box plot looks pretty symmetric, except there's a low outlier and a high outlier, so that might be a bit of an issue. When I look at my histogram, it looks more or less unimodal, like there's one high point. It's more or less symmetric. These data look to be reasonably normally distributed. If in doubt, go to Stat Basic Statistics and run a normality test, as I indicated in some previous set of notes. So I want to do a normality test, length to width ratio. Usually I like to use the Ryan-Joyner test because it's used for smaller sample sets, which is what we have right here. And from a visual perspective, I want to know whether these blue points fall along this red line. They're not too bad. There's a few that fall off the wagon. Ultimately, however, we look at this p-value, and somewhere in one of your sets of notes it tells you that if your p-value on this test is greater than 0.1, the data are quite normal. The only time you really got to worry about it is if the p-value is smaller than 0.05, which is not the case with these data. Now, going back to our question, so we've addressed parts A and B, and we just looked at the graphs. It would appear that these data meet the assumptions of the test because our data have to be reasonably symmetric. That looks good, or reasonably normal, I should say. And the last part of the question is, what are the practical implications of our results? Okay, well, what are our results? We have concluded that these bones do not represent species A. There's some other species. But it's possible that we've made the wrong decision. Now, how likely is it we've made the wrong decision? Not very likely, because that's where that p-value comes in. That's the probability I've made the wrong decision. That's pretty low, so most chances are I'm making the right decision. But it's possible that I'm making the wrong decision. How could that be? Well, let's just say it's 5 million years from now and the human race no longer exists. And the Martians finally land on planet Earth and they dig up the tallest man, woman that ever lived on Earth and their family. And those are the only bones that they dig up. Are the Martians going to be able to make adequate conclusions about the entire human race? Let's just say they were looking at the height. Would they be able to make adequate conclusions about average height of the human population if all they have are the bones of the tallest people that ever lived? No, they're not. So every time that you're making conclusions, you need to have in the back of your mind that it is possible that you don't have a representative sample. And if that's the case, conclusions may not necessarily be valid.